So with that, now let's go back to sort of the way we wrote down the original equations of motion, right? So remember when we derived the momentum equation, again in the video, right, we had a normal vector. We did everything in the current configuration, right? Now let's do it in the reference configuration. So now we have an N in the reference configuration, a big T in the reference configuration, some body force in the reference configuration. I'll use a big V for that. There's a big V for that. We also have a density in the reference configuration and a volume in the reference configuration. So let's just write down the terms, right? We have that, oh, and by the way, we have DSO, right? So we have, or big S, big S. So we have the integral T d big S plus the integral of rho b dv0, right? So now we're just doing the same things, right? We have the force, the surface forces integrated over the surface of the reference configuration. We have the body forces integrated over the volume of the reference configuration. And then, remember we had this, using Reynolds transport theorem, we had d dt, the integral rho 0 v dv0 now, right? So this is the total linear momentum. This is the total linear momentum in the reference configuration. Right? We're going to take the time derivative now. So sum of the forces is equal to the change in linear momentum, right? Let's use the divergence theorem on this thing. Oh, I should have a normal vector there. You guys let me. So, T in ds, right? Which of course is P transpose. Or, I'm sorry, what am I doing? I was trying to, I had it right the first time. All right, so we have T ds, okay, which we have an equation for, right? So this is P transpose N, okay? And then we can use the divergence theorem, right? So then when we do that, we have the integral of P transpose dv0 plus dv0 equals to d dt dv0. Okay. Okay, now just one subtlety here. Remember when this whole nonsense about the material time derivative and the ddt came about via Reynolds transport theorem because I'm taking the time rate of change of an integral that's over a volume, and the whole thing was that the volume might be changing, right? But here, by definition, it's the reference configuration. It's not changing, right? So I can just move that inside there, and I mean, if just for consistency, what will really, well, I'm trying to leave down here room for the final equation. So, you know, this is equal to rho 0 dv dt dv0, right? And it's because this, I don't really need to use Reynolds transport theorem. I can just move that guy inside because this volume's not changing, right? But if we want to keep them, there's no harm in keeping the notation of the material time derivative, right? Because the material time derivative is in spatial coordinates, So if I were to just write down dv dt, which of course is equal to dv dt plus v, that's v, plus v, and then to be explicit, grad little x v. Right? Well, now I don't, this term is 0. So there's no gradient with respect to little x because everything's in terms of big X, reference configuration. Right? So we can still use the notation the same, and it sort of unifies the way the equations look. So I'll just write down the final equation as rho dv dt is equal to the gradient, and just to be explicit, it's with respect to big X of P transpose, right? By the way, this is because there's this equation has to hold for arbitrary volume dv0, right? So then all of the integrands must be equal. So we have this, or remember P transpose is the first Biela-Kirchhoff stress, so we can say dv dt is equal to grad x first pk plus rho 0 b. So in the end, if you just sort of ignore the 1 pk, then you get an equation that's, it looks identical to the first one, right? The Cauchy momentum equation. You just ignore that. You get something that looks, except the only thing that this b would be little b. But other than that, I mean, it's the same, which is nice. You only have to remember, if you can remember this, right? Then it just, if you're in the reference or the current configuration, you just have to remember what the definition of the material time derivative would look like and what this gradient is with respect to. Right? And so, and of course, because we have this relationship, right? We didn't do it, but we could solve this equation for the Cauchy stress, right? So if I know the deformation, F, they're all related through F, right? This is F transpose, F inverse transpose. This is the determinant of F. So it's just the Cauchy stress times some function of F, right? Is the first Biela-Kirchhoff stress. Okay, so if I know the deformation, if I know F, I really can solve the equations however I want, right? If I have a constitutive model, and it really comes down to energy conjugacy, which we'll talk about later, that these stress terms are conjugate to different strain terms. And so if I have a Cauchy stress, which is energy conjugate to the rate of deformation tensor, I can formulate my constitutive model that way, okay? But then let's say so I can have a constitutive model, I can formulate it that way, but then let's just say that I want to actually solve the equation with respect to the reference coordinates. Then I have the Cauchy stress, I just plug it in here. I have the Cauchy stress and I have the deformation. I just plug it in here, I get the first Biela-Kirchhoff stress, I plug that in there, and I solve the equation this way, taking gradients with respect to big X. So they're all related. You just have to be consistent, or you have to understand how to be consistent between them. Now, just one last